So, welcome to the lecture 22. Here we can explain simulation flow chart with the state and rate variables. So, you know this the state variables, they are the core of a crop modeling. So, the model having the more number of state variables is known to be robust models. We have so now here we will discuss this potential production simulations, and we can see the flow charts of the state and rate variables. That means, how the variables are interconnected and how the flow process goes from the one compartment to another compartments. So, as we discussed for the water tank examples, we have discussed the flow of water from one tank to another tank, inflow and outflow. So, then there is a change in the volume of water in tank 1 with respect to time. The state variables have the changes with respect to time in a particular tank because of the inflow rate minus outflow rates, and also you have represented this in a flow chart. So, flow chart gives a proper understanding about the interconnections among these variables and how the dependence of the variables on several parameters or the constants or the other variables, that also explained in this flow chart. So, here this lecture, so we will be explaining about the potential production simulations with these flow charts. So, please have a look at this. This is the overview of the crop simulation flow chart. If you see this one, this is the Forester notation. The compartment model symbols are here used for this for representing this potential production simulations. Here mostly we are explaining the effect of the weather parameters, because the potential production simulation, the inputs are the weather parameter, as we explained the just previous last class, where the weather parameters, they influence the crop growth and yield. Other like water and nutrient modules are switched off and the plant protection also switched off. So, they are assumed that they are all in optimum. The crop does not suffer from water and nutrient stress, and the crop is well protected from pest and diseases. So, here mainly the yield is influenced by the weather parameters. So, this presents the potential production crop models. They integrate the environmental inputs, physiological processes and plant growth. The major components are, in case of potential production simulations, photosynthesis and assimilations. Now, the conversion of carbon dioxide to carbohydrate, and this assimilation, that is to biomass. Then growth and the respirations, biomass partitioning, developmental progress. So, these are the things which are the major components of the potential production simulations. How the photosynthesis is definitely influenced by the weather parameters, solar radiation, temperature, we will explain here, and the this photosynthetic assimilates, that is then the growth goes on, because the assimilate converted to dry tissue. On the carbohydrates is converted to tissue formation, that makes a growth, and through respiration, loss of respiration through carbohydrate, then the growth formation. After the growth, the total dry tissue, dry biomass, it is partitioned to different plant parts, maybe the leaves, stems or the root parts, or different plant parts, the partitioning of the biomass, and that also influenced by developmental stage, how the developmental stage progress also is influenced by this developmental stage influenced by the weather parameters like temperature. The model operates under the non-limiting water and nutrient condition. Also, the model operates under the no biotic stress, particularly the crop does not suffer from water and nutrient stress. So, if you see this one, this is the flow chart of the potential production simulations. From here you can understand from the compartment models, definitely these are the rate variables. This is the rate variables, potential assimilations Pg, this is the rate variables, and maintenance respirations, this is the rate variables, growth rate, this is the rate variables, and this is developmental rate, this is also rate variables. So, just 1 minute please, I will make the pointer. So, this is rate variables, that is a potential assimilations rate variables, and this is the maintenance respiration rate, this is the rate variable, the growth rate, this is rate variable, and development rate, this is a rate variable in this model. So, these are the 1, 2, 3, 4 rate variables in this model. What are the state variables? State variables are represented by the rectangles. If you see the state variables are canopy dry weight, this is a state variable, root dry matter, this is a state variables. So, that gives a quantity. Rate variables, the suppose biomass, this is per unit time, per unit area per unit time, you can say the rate variables. The biomass, the gram tissue per meter square per hour. So, this is the rate variable, but here the biomass is gram per meter square. This is the state variable, and this is the state variable root dry weight gram per meter square state variable. So, these are the represented by rectangle. Developmental stage, this is a state variable that varies over time, because the crop may be at particular time, depends upon the leaf number or the node formation. Crop may be at tearing stage, then moves to the panicularization stage, then moves to flowering stage. So, these are the developmental stages. This is a state variable that changes with time as the progress of the crop. So, the developmental stage changes, transformation from one stage to another stage. And also you can see the rectangle, these are the 3 rectangles are state variable. You can see another state variable here, assimilates. After the potential assimilations, the amount of carbohydrates assimilated during photosynthesis, we can say photosynthesis we can say, and some carbohydrate lost through respirations. So, there is a net assimilations, but why you do not consider this one as a state variable, because say net assimilation that is immediately converted into dry weight growth rate. So, there is no accumulation of this one assimilate. So, this is converted to dry weight growth rate through conversion efficiency, that means the. So, as based upon the potential assimilates, that is a conversion to dry biomass. How much carbohydrates is converted to dry weight as a conversion efficiency, immediately is converted to the dry weight as a root tissue, dry tissue. So, we do not consider this as a state variables, because there is this is a temporary one. For understanding the assimilates, is particularly converted to dry weight, and this is a partitioning as a canopy. Ultimately, this get partitioned to canopy and the root. These are the state variables. So, in this model there are 3 state variables mainly, the canopy dry matter, root dry matter, and the developmental stage. These are 3 state variables, and these are the rate variables: potential assimilation rate, maintenance respiration rate, and growth rate, and the developmental rate. These are the 3 state rate variables. So, these are symbols represent, and also you can find here some of the dotted lines and some of the continuous line, bold line. So, as you see the model, the dotted line represent the pathway for the information flow, and the solid line the pathway for the can see material flow. So, the assimilation there is flow, because this information flow where the temperature, weather parameters, and the effect is dependent, because on the effect what is the parameters or the coefficient, they influence the rate of the rate of the system. So, those are represented by this either the these symbols. So, that will be explaining in the next slide. You see the how the environmental inputs and the control variables. These are the light, radiation, you can say radiation, or the temperature, or the photosynthesis and how they influence the potential assimilates. The photosynthetic parameters also so let us have a light, the light that interceptions that depends upon the leaf area. You can see the leaf area as discussed earlier, the intercepted light radiations IR, or the intercepted photosynthetically active radiation, we can say the PAR into 1 minus e to the power minus k into LI leaf area index. So, leaf area that influence the intercepted light, this is the intercepted light. If the light, there is a light interception, and light interception that influence the potential assimilation. The potential assimilation is influenced by the light interception, that is a radiation, light means radiations, the radiation interception by the crop, which is ultimately influenced by the leaf area, and leaf area is regulated by the developmental stage, because leaf area varies over the time, and the leaf area, the particular stage of development, the leaf area depends upon the developmental stage leaf area, and this potential assimilates that is influenced by this light and the light intercepted lights through leaf area, that influence the potential assimilation. Of course, this is also influenced by the temperature also that influence the potential assimilation rate, because it is optimum temperature, the process is particularly the optimum one, you can say if the temperature remains beyond optimum, the process is less than 1 or more, say greater than 0. There are also some photosynthetic parameters also that influence potential assimilation. Similarly, I can see you this is the how the things are influenced here, this is how the light is influencing here, and see the temperature that control the developmental rate. The temperature, so repeatedly I am also explaining the radiation that contribute the biomass accumulation and temperature that contribute to the crop development. That means, the radiation biomass accumulation is growth. Radiation is the main weather parameter for the growth of the crop, and temperature that influences development of the crop. Growth and development is a continuous process, they should go on, because there is a proper growth and proper development that leads to the optimum biomass production and so also the yield. So, this is the temperature that influence developmental rate, RM and RT we will discuss also in later classes, and the developmental rate that influence the developmental stage. Developmental rate means number of leaf appearance per unit time. So, once they accumulate the number of leaves, number of nodes formations, then the crop transfer from one stage to another stage, the developmental stage. So, this developmental stage that also regulate the, because leaf area index will be changing of the developmental stage, and the then we discuss the partitioning, because the partitioning from the biomass to the root and the shoot, that also the function the amount of biomass, how much to be partitioned to the cannabis dry matter and the root dry matter, that depends upon the developmental stage. So, that will be coming. So, now here we see the light and the temperature, the light particularly radiation that influence the radiation interception by the crop and ultimately the potential assimilates, and the temperature that influence the developmental rate means leaf appearance, how much leaf appearance, node appearance, developmental rate, and ultimately the developmental stage. Then also this potential assimilate is influenced by the photosynthetic parameters, particularly carbon dioxide response of the crop, temperature response functions. This already give link this one, how these are also they influence this photosynthetic parameters, influence the potential assimilate. That means, the amount of carbohydrate assimilates per unit area, unit time, gram carbohydrate per meter square per hour, that is potential assimilation rate. This is the rate variable. And similarly, the potential assimilation, this is the gross carbon. See the potential assimilation, the gross assimilates grams CH2O carbohydrate per meter square per hours, that is a rate variables. So, this is maintenance respiration carbon loss, amount of carbon lost. How the maintenance respiration? That is dependent upon the you can say temperature, that is influenced by the temperature and the other parameters, light and temperature, maintenance respiration, and this also depends initial dry weight of the crop. Maintenance respiration means amount of loss of the carbon per unit carbohydrate, gram CH RM into W. So, amount of the maintenance, how much carbon is the lost in the process, the carbohydrate lost in the process, the carbohydrate accumulation, carbohydrate lost in the process to maintain the original plant tissue per plant tissue. So, gram tissue, gram CH2O lost per the gram tissue. So, the plant has because plant has original dry weight, to maintain this dry weight. So, the per maintenance means respiration means there is a loss of carbohydrate, the process where the respiration goes on, the plant takes oxygen, releases carbon dioxide. So, this process there is a loss of carbohydrates to maintain the original plant tissue or original plant weight. So, this is a loss of carbohydrate, if you see, and through that the plant gets huge energy for different processes. See, human being also what happens now, if you see, if you are climbing a stairs, so your breathing becomes very fast. That means you are in that case, because through that breathing you get energy for climbing stairs. Plant needs energy, and plant gets energy through respiration. That is why I am saying the plant must sleep. It is sleeping time, the plant sleeping time, and sleeping times accumulate energy for the like human being, you need the daytime work and night time for sleeping, because if you sleep and then the next morning you get energy for the work. Suppose you do not sleep night time, daytime you are working, night time you are awake. So, there is no sleep. So, you will not get proper energy for the next day or the next morning work. So, in plant also, plant during daytime they are busy for making photosynthesis. So, creating the biomass productions, biomass assimilation, their plant system remain very busy for the receiving carbon dioxide, converting carbon dioxide to carbohydrate. So, plant system remains quite busy for the food productions during the daytime. During night time is a rest, respiration goes on during night, the rest time, and in that process the plant accumulates some energy, and that energy for the different systems of the work. So, plant must sleep. If there is no sleep, there is no night time, no dark periods, then the developmental stage is affected, the crop may not transform, because it may take longer time for transformation from one stage to another stage, and also so it may influence the growth of the crop. So, night time respiration is must for the plant. So, that is why the then after this the maintenance respiration, there is a growth rate. So, growth rate is the so the potential assimilation minus the respirations loss. So, there is a net assimilate. This net assimilate is converted to particularly the canopy or root dry weight through this growth conversion efficiency. So, whatever the assimilate carbohydrate has, almost depends upon the conversion, how much is converted to the growth rate, the dry tissue formations. The carbohydrate is converted to dry tissue formations. So, that is a conversion efficiency. Then the rate variables control the speed of change in the system. So, the state variables see there are the biomass partitioning. So, as I discussed, there are mainly the 3 state variables. Canopy dry weight, this is the canopy dry weight state variable represented by the rectangles, and the root and dry matters and the developmental stage. So, these are the 3 state variables, and this is the dry weight growth rate after the conversion of the assimilates to dry weight growth rate, and that get partitioned. Amount dry weight assimilate, because as carbohydrates is converted to biomass. The amount of carbohydrate accumulated by the plant through the process of photosynthesis, those carbohydrate is converted to tissue formation, it is a biomass, and the biomass is partitioned to the root dry weight and the above ground dry weight. So, either the root dry weight is the above ground dry weight, root is the below ground portion, there some biomass partition to the root portions, root dry weight, and some may go to the canopy dry weight. And the partitioning, what the function partitioning, how much suppose the plant accumulates, the partitioning 60% goes to either 60% goes to shoot, the canopy, and the 40% goes to root, or 40% goes to root, or 60% goes to shoot. That depends upon the developmental stage of the crop. At the beginning stage of the beginning, probably the conversion, the partitioning of the biomass from the to canopy and the root, that is a function of the stage of development. So, not constant throughout the growth phase. So, how this is calculated based upon the experimental understanding, experimental finding. This calculated the total biomass accumulated, the percentage of biomass that transfers that partition to the root, and how much biomass that goes to the shoot portion. So, that is not constant throughout the growth period. So, that depends upon the developmental stage of the crop. Then the state variable that system memory over time definitely. So, partitioning the allocated biomass between the canopy and the roots changes with developmental stage, that is not the same throughout the growth periods. So, leaf area links biomass accumulation with the light interception, definitely I discussed earlier. So, light interception depends upon the leaf area. So, these are the interrelations between the variables, you can say how the state variables, rate variables, and how they are influenced by the other parameter. This is clearly explained in this flow chart. So, here the developmental rate that influence developmental stage, and the developmental stage that influence the as a partitioning, how much biomass to be partitioned to the canopy, how much partition to the root portion. And this the loss of carbohydrate maintenance respiration, that is influenced by this weather parameters. At the same time, this is also influenced by this canopy dry weight. This is the state variables original canopy, initial canopy dry weight. Original means initial canopy dry weight. When there is a accumulation, suppose today there is a dry weight 15 gram per meter square. So, after 10 days the dry weight changes, and the dry weight changes means that is because the carbohydrates gets converted to the dry biomass, and the dry biomass partitioning takes place, that depends upon the initial dry weight of the crop, how much is the carbohydrate lost and how much is assimilation converted to the dry weight. So, here we can say this crop growth is simulated through interactions between the state and the rate variables. So, as you have seen, environmental inputs regulate photosynthesis and development. Biomass accumulation depends upon the carbon gain, respiration, and the allocation of rules different components. Development stage provides feedback control on leaf area and partitioning. This flow chart forms the core structure of the potential production model. So, as you see here, so this is what we are displaying. So, if you see the flow chart and if you recall this compartment model symbols, how they can be utilized to make the flow chart. This flow chart makes a very simpler understanding, and that gives understanding how the input the variables, the state variables, rate variables, they interact, how the flow takes place, flows from one compartment to another compartment, how there is a inflow and outflow. The inflow and outflow I can say rate variable. Suppose there is this is a potential assimilations rate, and there is a loss, then this is the final assimilates, that is the state variables. The amount lost from the amount accumulated, amount lost the final assimilate, but this assimilate is not accumulated, thus immediately get converted to the dry weight tissue, and the conversion, how much conversion, this is E conversion, the Pg minus Rm into W, the assimilates minus Rmw into conversion efficiency, that gives the dry weight growth rate, how much dry growth gram per meter square per hour, and that is converted, then there is a partition to the canopy dry weight or the root dry weight. So, that depends upon the partitioning functions, and that depends upon the developmental stage. So, the point we are discussing here, when there is we are going for the potential production simulations, and the simulation depends upon the weather parameters, solar radiation, temperature, and other photosynthesis weather parameters. They mainly regulate the carbon dioxide content, different contents, they regulate the growth and development of this crop. And this picture shows the effect of radiations, particularly for the light interceptions, then how that influence the potential assimilation rate, carbohydrate accumulation rate. Also, this is influenced by the other parameters like temperature and the photosynthetic parameters. Once you get the potential assimilations, then there is a loss of carbohydrate. So, loss of carbohydrate, that depends upon the again the weather parameters, maintenance respiration rate, and also that depends upon the initial crop weight. How much carbohydrate is lost through respiration, that depends upon the initial crop weight. You can see the that also you can say the crop is the early stage, there is a less accumulation of carbohydrate and the less lower initial weight and maintenance of lower initial weight, there will be lower loss of the carbohydrate for the maintenance. If the crop is at the peak growth stage, more biomass, that is also more assimilation of the carbohydrates, and to maintain that biomass, original biomass, there also will be more loss of the carbohydrate. So, this loss of carbohydrate that depends upon the canopy dry weight, initial dry weight of the crop. To maintain this dry weight, there is a loss of carbohydrate. This is the net assimilations. This net assimilation get converted to dry weight growth rate through conversion efficiency. They are converted to dry weight growth rate, and this dry weight growth rate, total dry weight including your root and shoot weight, and that is converted to the canopy dry matter and the root dry matter, and this based upon the partitioning. The partitioning that depends upon the stage of the crops. The crop is at what stage. So, these are the this flow of this materials, the flow of materials, a solid line, all the biomass that is converted to canopy dry weight and the root dry weight. So, these are the processes, particularly for the potential production simulations, and using this through this this gives a better understanding about the flow chart. So, if you go for any crop model simulation, either the soil water or the any growth process, nutrient balance. So, this flow chart can be utilized through the flow chart, that gives a better understanding of the input, the interactions among the state variables or the rate variables, and how the variables are influenced by the different parameters or different variables of variables. So, that this gives a understanding about the processes, how the flow of the processes, and which knowing this, it is a clear cut idea, and the factors, which factors are affecting the what factors, how the state variables are dependent upon the several parameters, and the flow takes place in the systems, and finally, to get the biomass and yield formations. So, this is the for the potential production simulations. This for an examples. We are not going to will be moving to the DSAT models, but this example sets the use of the flow charts and use of the compartment model symbols that make an understanding. They make a clear cut idea the cause and effect relationship. What is the cause, how the effect, how the inputs they interact with each other, how the flow of process takes place among the variables in that model. So, this is the flow chart. I hope this will give a clear understanding about the biomass simulations, particular biomass simulations, and how this depends upon the other parameters, like light and the radiations and the temperature or the carbon dioxide content in the atmosphere. They influence the potential assimilates, and how the loss happens through maintenance respirations, then the net assimilate accumulations, and the conversion of the net assimilate to the dry weight, and the partitioning of the dry weight, total dry weight, the canopy dry weight and the root dry weight, and when you go for the yield formation, that comes from the canopy dry weight. That will be explaining, of course, the later classes, how there is a yield formation from canopy dry weight to the yield formation. So, this is the particularly the use of the compartment model symbol to represent a potential production simulations. I hope this has been clear to you. With this, I thank you all. Thank you.